Hello! In this video, we are going to prove the following theorem. Suppose n is an integer greater than or equal to 2, and a and b are sets. Suppose 1 is an element of a, n is an element of b, and every integer between 1 and n is an element of a or b. Then, there exists a pair of adjacent integers between 1 and n. I'll call them j and j plus 1, such that j is an element of a, and j plus 1 is an element of b. Now, to sort of visualize what's going on here, let's consider a path of at least 2 points. Let's say that one of the endpoints of the path is red, and the other endpoint of the path is blue. And let's say that we also know that every point in this path is either red or blue. If this is what we know, then it turns out there exists a pair of adjacent points in this path, one of which is red, the other of which is blue. And the red point is going to be on the side of the path containing the red endpoint. The blue point is going to be on the side of the path containing the blue endpoint. And so if we enumerate these points 1 through n, well then, we'll say to be a red point means we're an element of A. We'll say to be a blue point means you're an element of B. Well then, we must be able to find a pair of adjacent integers between 1 and n. We'll call j and j plus 1, such that j is an element of A and j plus 1 is an element of B. So that's really what's going on here visually. So now, let's get into proving this theorem. Now the whole goal is to show that there exists a pair of adjacent integers between 1 and n. I'll call them j and j plus 1, such that j is an element of A and j plus 1 is an element of B. And to show that, we're going to split this up into 2 cases. Either n is equal to 2 or n is greater than 2. Let's first consider the case n is equal to 2. If n is equal to 2, well then we have 1 is an element of A and 2 is an element of B. So taking j to be 1, we have that j is an element of A and j plus 1 is an element of B. So we're done. So this completes the case n is equal to 2. Now let's consider the case n is greater than 2. If n is greater than 2, then the idea here is to consider the following set. We consider the set S, which consists of the set of positive integers x, such that 1 is less than x is less than n, and we have the property that x is an element of A. Now, we split this up into 2 possibilities. Either S is empty or S is non-empty. Let's first consider the case S is empty. Well then notice, we know that 1 is less than 2 is less than n. So 2 satisfies this condition, but is it also true that 2 is an element of A? Well, what happens if 2 is an element of A? Well then 2 satisfies all the requirements to be an element of S, so 2 is an element of S. But that contradicts the fact that S is empty. So it can't be the case that 2 is an element of A. We must instead have 2 is not an element of A. But we know that 2 is an element of A or B. So since we know 2 is not an element of A, we must have 2 is an element of B. So we have 1 is an element of A and 2 is an element of B. So taking j to be 1, we have j is an element of A and j plus 1 is an element of B, so we're done. So this completes the case where S is empty. Now let's consider the case where S is non-empty. If S is non-empty, well then S is a non-empty finite subset of positive integers. And every non-empty finite subset of positive integers has a largest element. In fact, that's true for any non-empty finite subset of real numbers as well. So S must have a largest element. And we'll call that largest element Q. Now, since Q is the largest element of S, well then of course Q is an element of S. So we know that Q is an integer such that 1 is less than Q is less than N, and Q is an element of A. And since Q is less than N, this implies Q plus 1 is less than or equal to N, because we're working with integers here. In general, when we have any two integers, S and T, then to say S is less than T is equivalent to saying S plus 1 is less than or equal to T. Right? This is true when we're working with integers. So in our situation, we can conclude that Q plus 1 is less than or equal to N. So we have 1 is less than Q, which is less than Q plus 1, which is less than or equal to N. Now the claim is that Q plus 1 is an element of B. And to show that, we're going to split this up into two cases. Either Q plus 1 is equal to N, or Q plus 1 is less than N. Let's first consider the case Q plus 1 is equal to N. If Q plus 1 is equal to N, well, since N is an element of B, we immediately have that Q plus 1 is an element of B. So this completes the case Q plus 1 is equal to N. Now let's consider the case Q plus 1 is less than N. Well then, we have 1 is less than Q plus 1 is less than N. So this tells us that Q plus 1 satisfies this condition, but is it also true that Q plus 1 is an element of A? Well, what happens if Q plus 1 is an element of A? Well then, Q plus 1 satisfies all the requirements to be an element of S. So Q plus 1 is an element of S. But since Q is the largest element of S, that means Q is greater than or equal to every element of S. So that would imply Q is greater than or equal to Q plus 1. But that's clearly false because Q is less than Q plus 1. So assuming that Q plus 1 is an element of A leads us to a contradiction. So we can't have Q plus 1 an element of A, we must instead have Q plus 1 is not an element of A. But we know that Q plus 1 is an element of A or B, so we must have that Q plus 1 is an element of B. So this completes the case where Q plus 1 is less than N. And what we see here is, in either case, whether we have Q plus 1 equal to N or Q plus 1 less than N, it follows that Q plus 1 is an element of B. So, putting this together, we now have Q is an element of A and Q plus 1 is an element of B. So, taking J to be Q, we have Q is an element of A and Q plus 1 is an element of B. So we're done. And so this completes the proof. Because we've exhausted all possibilities. In one case, if we have N is equal to 2, then we found a choice for J. Otherwise, in the case N is greater than 2, well, we consider two possibilities as well. If S is empty, then we found a valid choice for J. If S is non-empty, then we found a valid choice for J as well. So we've exhausted all possibilities. No matter what, we're able to find a choice for J such that this happens. And so yeah, that's pretty much it for this video.